Previously we've seen that one possible configuration of an electric and a magnetic field that satisfies the four Maxwell's equations is that we have a region in space, and this is a really large region as far as this length is concerned, and as far as this length is concerned, and as far as this width is concerned. So it's a large region in space, it's a slab of energy. Inside there exists an electric field that is uniform and pointing in, say, the vertical direction. It's the same everywhere, and alongside this electric field there is a magnetic field. That magnetic field is pointing out of the plane of the blackboard, and it's uniform, and there exists no electric field after or before this slab of energy, and this entire slab of energy is moving forward with a speed v, a uniform speed v, which turned out to be the same as, it's of course electromagnetic energy, so it's equal to the speed of light, and this turned out by a stroke of fortune that this equals epsilon naught over mu naught under root. So energy which is present in electric and magnetic fields in such a manner that the electric and magnetic fields are normal to one another, and this entire slab of energy is moving forward with a speed, a precise speed given by this constitutes an electromagnetic pulse, a pulse of energy, a combination of electric and magnetic fields, a configuration of fields that satisfies Maxwell's equations. This is called an electromagnetic pulse, since it comprises electric and magnetic fields. Now mu naught is defined by the definition of an ampere. So you have two current carrying wires which carry 1 amperes of current each. You can find the force between these wires, which can be measured. That defines an ampere, and the force is given in units of mu naught. So mu naught is defined. C is defined by a standard of a meter. So C has been defined to be precisely equal to 2.99792,458 into 10 to the power 8 meters per second. So this defines the speed of light because it's given by the definition of a meter. Likewise, you can calculate what epsilon naught is, what the permittivity of free space is. But nevertheless, you do recognize that this slab of energy is moving forward with the speed c, the speed of light. And it can only move forward with the speed of light. There is no other speed that's possible. So this speed of light, c, turns out to be a universal constant. Now consider the following scenario. I have a slab of energy, and I have neighboring slabs of energy. And I have many of them. And in each slab of energy, I have an electric field. Now I'm just drawing one vector inside this entire slab, and I'm assuming that the field is uniform inside this slab of energy. And this electric field E is pointing upwards. Here it's also pointing upwards, but it's slightly smaller in magnitude. Here it's 0. Here the electric field has started turning around. It's in the opposite direction here. It's still uniform inside this slab. Here it's gone up again, but in the opposite direction. Here it's gone up again. So consider this configuration of electric fields. You have adjacent slabs, and in each slab there is a uniform electric field. So when I draw this really means that inside this entire region the electric field is going to be pointing in the opposite, in the negative direction. And all of these field vectors are of the same length. So it's a uniform field, but only inside this slab. Now this amplitude of the electric field is oscillating in space. And this entire region of slabs is moving forward with the speed c. This speed once again is given by 1 over mu naught epsilon naught under root. Now in each of these regions, of course, there exists a magnetic field as well, because without a magnetic field you cannot satisfy Maxwell's equations. That magnetic field is perpendicular. Now the direction of the magnetic field here is outwards. Here it's also outwards. Here the magnetic field has dropped to 0. Here the field has gone inwards. Inwards. Still inwards. And if I were to draw a perspective view of the magnetic field vectors, this is a large field pointing outwards. This is a smaller field pointing outwards. Here the field is 0. Here there is a small field pointing inwards, a larger field pointing inwards, and an even larger field pointing inwards. So this is a snapshot of the electric field and magnetic field configurations at one point in time t naught. So now if I were to draw a graph of, on one axis I take space, x, and on the other axis I take the amplitude of the electric fields. Here the electric field is some height, here the electric field is some lower height, here the electric field has gone to 0, here it's changing its direction, here it's increasing in the opposite direction, here it's gone up again. Now if I make these slabs really closer, thinner and thinner and thinner and thinner, all of these slabs will still satisfy Maxwell's equations, because each one of these slabs is satisfying the 4 Maxwell's equations. So what I could actually construct is a waveform that represents a harmonic wave, an oscillatory function in space. So this is, if I make this finer, if I make the scale finer, which means that I make the slab smaller and smaller and smaller, then what I could get is a wave in which the electric field has an oscillatory amplitude. So this is my position variable, and this is the magnitude of the electric field. So it's going up in some regions, then it's dropping in some other regions, it's going up in the opposite direction, and so on and so forth. So this is an oscillatory electric field in space. This is what we call generally a sinusoidal harmonic, a sinusoidal or a harmonic electromagnetic wave. Now this wave will satisfy the 4 Maxwell's equations, because each one of these slabs is satisfying the Maxwell's equations. And this wave is propagating forward with the speed c. Since it's propagating forward with the speed c, if I fix my position at x naught, and I find out how does the electric field that's hitting me at x naught change with time, I will again get an oscillatory function, because all of these slabs are coming and rushing through me one after the other. The electric field is going up, down in a harmonic fashion. So I could also make a plot of the electric field with time on this axis. Such a plot will also look like this. I have time on this axis and I have an electric field. Now this is the time axis. So now this is the snapshot of the electric field configuration at some fixed x naught. This distance between two crests is called the time period. And from here I define a frequency. This is the frequency of the electromagnetic wave. This distance between the two crests in the position variable is called the wavelength. And this wavelength and the frequency are related like any other wave through this relationship. C equals F lambda. This is what we generally call an electromagnetic wave. And this satisfies all 4 Maxwell's equations. It's a special kind of an electromagnetic wave called a plane wave. You could also have waves of this kind. If I have the x variable here, you can have an electromagnetic wave in which the electric field is constant, then it suddenly changes its direction and it remains constant in the opposite direction and so on. So this is just a slab of energy in which the electric field is pointing upward, then a slab of energy in which the electric field is pointing downwards, upwards, downwards, and these entire slabs are moving forward with the speed of light. This is also a possible electromagnetic wave. There's no harm in having such a wave, even though it's difficult to produce such a wave because of these sharp boundaries in the electric field. And remember, in the case that I've drawn here, if I were to plot the magnetic field versus x, I will get a similar graph with the same wavelength, with the same frequency, the same time period. So this is the magnetic field plotted at some fixed time t0. Concomitant with this electric field, there is a magnetic field. Concomitant means alongside. Both of them go hand in glove with one another. If there is an electric field, there has to be a magnetic field. And the relative orientation of these electric and magnetic fields is given by the following. You have an electric field and a magnetic field. And both of them are normal to one another. And this entire slab of energy, chunk of energy, is moving forward with some speed, c, which is a vector, it's a velocity. And this c is given by the cross product of E and B. If you have an electric field like this, and a magnetic field that's pointing into the plane of the black hole, then the propagation of this wave will be in this direction. So this is E, this is B. So the cross product of E and B is parallel to the direction of propagation of the electromagnetic wave. Propagation. So this is a basic introduction to electromagnetic waves and how they satisfy all four Maxwell's equations. Let's have half a minute of silence in honor of this. As I mentioned, electromagnetic waves are the zenith of electricity and magnetism because they combine all four Maxwell's equations, all four of them. They satisfy all four of the Maxwell's equations. They were discovered invented or discovered or produced for the first time in 1887 by Hendrik Hertz, who produced radio waves. And you know what the electromagnetic spectrum is. It ranges from gamma rays, X-rays, all the way to infrared. It's a huge spectrum of light. Generally it's called light, just light. So what I would like to now talk about is how do we produce such a configuration of electric and magnetic fields? Right? Because we have to transmit an electromagnetic wave. So we've seen that there is a certain disposition of electric and magnetic fields that is required, and this is the relative orientation of these fields. But how do we produce such fields in the first place? How do radio transmitters work, for example? Now what happens is, suppose I have a charge, a positive charge that is at rest. If I plot the electric field lines for this positive charge, they are all radially outwards. Is the field uniform? Is the field uniform in this case? No, it's not. It's larger near the charge and it drops off as 1 over r squared far away from the charge. So for a static charge, the electric field's dependence is 1 over r squared according to Gauss's law or according to Coulomb's law. So this is a static charge. Now if I have a charge that is moving at a uniform speed v. So now I show a static charge, therefore I show a wake of this charge. So this charge is actually moving with a uniform speed towards the right. Now I would like to plot the electric field of this moving charge at an instant of time. Now what's going to happen is, now relativity kicks in. Now according to special relativity, every moving object, if you're in a frame and you see a moving object, the length of that object is contracted. It's called the Fitzgerald contraction, Lorentz contraction, according to which this electric field remains radially outward but is no longer uniform. In this case it's not uniform but at a fixed radius. At least you know that along this radius the electric field is going to be the same on this radius. But that scenario now changes for this electric field. What's going to happen is that the electric field lines are going to bunch together in a plane that is normal to the direction of the propagation. So they're going to bunch together inside this plane. They're still going to be radially outwards. They're going to spread out or thin out as you go away from, as you go towards the direction of propagation. So this is the direction of the propagation. This is a plane that is normal to the direction of the propagation. These electric field lines are going to bunch together towards the plane that is normal to the direction of propagation. And this results from the contraction property of the length contraction in special relativity. So this is the field due to a moving charge. At a fixed angle, the field still varies as 1 over r squared, but no longer is it the same as at a fixed radius on this circuit. Here the field is larger because this is a plane that's normal to the direction of propagation. So this is what the field due to a moving charge which moves with a uniform speed looks like. So the electric field pattern can change depending upon your observation. If there is an observer who's sitting on the charge and moving with the speed along with the charge, that observer will see a radially distributed electric field just like this. It will not see this bunching of electric fields inside a plane normal to the direction of propagation. However, in the lab frame, an observer sees a moving charge moving with a velocity v. So these electric field lines are going to bunch together in a plane normal to the direction of propagation. Now we've also considered another concept called retardation. Now let's finally invoke this concept to look at something useful. Suppose I have a charge that's static. This is the electric field due to the charge. Alright, let me draw this configuration again. draw really light lines for a reason. Now this is a charge, static charge. It has been sitting there for a long period of time. So the electric field exists everywhere in space, even though it falls off as 1 over r square as you go really far away from this charge. Alright? So this charge has been perched in space and it's been sitting there for a long time. Now there is some source or stimulus that gives a kick to this charge in the downward direction. So it accelerates in the downward direction. There's a force on this charge which makes this charge accelerate or kick in the downward direction. So it moves, it picks up speed, it accelerates in other words, and comes to a new position. It's still accelerating, by the way, and I take a snapshot of this accelerating charge at some point in time. Now if I were to plot the electric field of this accelerating charge, if a charge were in this location and it had been sitting there for really long, then of course I would see once again a radially outward pointing electric field. But if I make an observation that this charge is now accelerating and I have an observer, suppose that observer is placed somewhere, say here, or here, or anywhere. Suppose the observer is at this location 1. This is location 1. Now the charge is accelerating downwards. What does the observer 1 observe? Now this observer is at a certain distance r from the charge. Now the information for an electric field transmits at the speed of light. This process is called retardation. If this observer 1 is at a distance r from this charge, and this r is smaller than the speed of light into the time at which I'm making an observation. So this charge has been kicked in the downward direction. Now I take a snapshot of the electric fields at time t, or let's say time t naught. I would like to find the electric field at this point number 1. There's an observer at point 1. If the distance of this object from the new position of the charge is r, and this r is smaller than t naught, c times t naught, then the electric field configuration of this charge will have propagated to point number 1. So at point number 1, the electric field that this observer is going to feel is in this direction. This is the electric field information from this charge, because this is the position of the charge. Correct? You see, the yellow lines show the electric field lines from a charge at time t naught that is in this position. The white lines show the older electric field at time t naught earlier. However, this point, this observer 1 is at a certain distance from the charge such that it has enough time for the electric field to propagate to this point in order to, so that the information of the new electric field has been transmitted to observer 1. So according to the new configuration of the electric field is pointing in this direction. So if I were to make a sphere around the new position of the charge at time t0, and the radius of this sphere is ct0, then the electric field will be pointing radially outward from the new position of the charge. Inside this region, the information that the charge has moved to a new position has been transmitted to all observers inside this volume. Correct? Because it takes a certain amount of time for information to transmit. The electric field does not change instantaneously when the charge reconfigures itself. The charge is reconfiguring itself, so it's producing a new electric field in space. That new electric field is given by the yellow lines. But this information takes time to travel. It's not an instant effect. It takes time to travel. The speed with which this information travels is the speed of light. So within this volume, any observer that is located inside the volume will see an electric field that is reflective of the new configuration of the charge. And that's radially outward from this new position of the charge. So within this volume, the electric field is going to be radially outward from the new position of the charge. However, if there is an observer at this location 2, this observer cannot notice that the charge has actually changed its position. So this observer will actually see a different electric field. The electric field this observer is going to see is going to be totally different. It's going to be reflective of the older position of the charge. And according to the old position of the charge, the electric field is pointing in this direction. Say we have a location 2 here. That's location 2 is here. So if this is location number 2, this is outside this radiation volume. This distance is greater than CT0. So at this location, the electric field that is experienced by an observer is reflective of the old position of the charge. At this location, if the information had transmitted, the new electric field would be pointing in this direction. It is going to be radially outward from this location of the charge. However, it just sees the old configuration of the charge because the information of charge reconfiguration has not yet transmitted to this point because it's at a larger distance away from the charges. That distance is greater than CT0. Therefore, the electric field configuration at some point in time is not going to point radially outward if this charge is accelerating. Instead, there will be kinks inside the electric fields. Let me try to draw a pattern of electric fields at some point in time t0. And then this will bring home the idea of retardation. So this is an old location of the charge. This is a new location of the charge. This is the direction in which the charge is accelerating. Now within a certain volume, the electric field is radially outward. Now at this location, outside this distance, the electric field is not governed by the new position of the charge, it's governed by the old position of the charge. And in the old position of the charge, the electric field at this location is going to point radially outwards from this charge. So it's going to point like this. Right? So at this location, above this point, the electric field is going to point in a direction that's radially outward from the older position of the charge. So outside this yellow circle that I've drawn, the electric field will actually point in a direction that's governed or deflected by the older position of the charge, because the information of the charge has moved, has not yet been transmitted to points outside this observation circle. So if I were to draw continuous electric field lines, if I had an observer here, he will see a shift in the electric field, a kink in the electric field. Here an observer will experience a kink in the electric field, a kink in the electric field, a kink in the electric field. Here an observer will not see any kink in the electric field, because this line lies in a plane that's perpendicular to the, that's parallel to the acceleration of this charge. Here one will also observe a kink, a kink. Now these steps are called kinks. Here there will be no kink. Here there's going to be a kink here, smaller kinks, slight kink, even smaller kink and kinks. So you will have a ring of kinks inside on this yellow circle. So let me redraw this diagram with a bit more clarity. So these are the electric field lines configured at some time t0, because this charge has been given a downward kick with the help of which this is accelerating. Notice that the kinks are largest along the direction of propagation and normal to the direction of propagation. Now, what propagation direction are we talking about? Okay, let's forget about propagation. Let's look at the acceleration. The acceleration vector for this charge is downwards. So in a plane which contains the acceleration vector, which is parallel to the acceleration vector, there are no kinks. However, in a direction that is normal to the acceleration vector, in this direction the kinks are largest. Now, if you take a picture of the electric field at some time t1, which is greater than t0, then what's going to happen is that the information that this charge has moved onwards, it has accelerated to a new position, has transmitted to even larger distances. So these kinks are shifting outwards, they are going radially outwards. So this sphere of observation is now expanding with time. And the speed with which this is expanding is just the speed of light, c. So this ring of kinks is going to dilate with time. So at some later time t1, if I were to draw this electric field pattern, the pattern will look like this. The kinks have now advanced in time. The kinks are now further away from these charges. So the kinks have now advanced to this outward position. Now the electric field lines are going to look like this. They're going to experience a kink at a position further away from the charges. If I plot this electric field, new electric field here, it's going to experience a kink at a point further away from these charges. Because now the new position of the charge is making its presence felt over a wider volume in space. So this kink is propagating in space with the speed of light. Now if you were an observer at this location, and if you were to feel the electric field, at this point, the electric field was just pointing towards you. So suppose I have an observer here. At some point in time, which is less than t0, there is no electric field. In fact, the electric field is just coming into you. There is an electric field, but it's coming into you. It's a longitudinal field. At some point in time, t0, a kink appears here, which means a transverse electric field is observed by the observer. An electric field that's pointing in the upward direction is felt. And then this kink advances forward, so the electric field drops to 0 again. So this is my time axis. At time t0, an electric field is seen. The observer will have a finite width. That electric field is going to exist for a certain period of time, and then it's going to drop again because the kink has moved forward. Remember, in normal circumstances, this point is seeing an electric field that's pointing radially outward, that's going through me. But at some point in time, I see an upward electric field. This is the kink. This is a transverse electric field. The kind of fields that are drawn over there. An upward pointing electric field. So this kink is actually the electromagnetic wave that is propagating outward with the speed of light. These transverse electric fields are the electromagnetic wave. So I'm an observer standing here, there's a charge, I'm just feeling an electric field going through me horizontally. That's always there, that electric field is always there. But then suddenly, because the charge is being kicked downwards, far away from me, I'm feeling its presence felt by an upward electric field. If I were a charged particle, I will see an upward force. I will jump up because of the upward electric field, of the transverse electric field. So if I were a charged particle here, I'm seeing an electric field which is pushing me backwards horizontally, but suppose I'm restrained, I cannot move in the horizontal position. Then I see an electric field, a surge of energy in the upward direction. There exists an electric field that's going to give me an upward jump. That's the transverse electric field, and that jump is disappearing because the kink or the ripple of energy is going forward. So that is just the slab of energy that I see. So around these points, I will see transverse electric fields. These are the electromagnetic wave. And associated with these electric fields are magnetic fields, because only a magnetic field that's normal to a transverse electric field can satisfy Maxwell's equation. So there is a magnetic field that's pointing in the outward direction here. This is the electromagnetic wave. And this is how electromagnetic waves are produced by accelerating charges. So if I accelerate this charge, I feel a transverse electric field, which is an electromagnetic wave. And here I've just drawn a two-dimensional pattern in a three-dimensional sphere. If I were to draw this in 3 dimensions, I will get a complicated diagram. Let me try drawing that diagram for you for a minute, and then I'll ask you a question. So I have a charge that is getting a kick, receiving a kick in the downward direction. Now if I were to plot only the transverse electric fields, I'm not drawing the radially outward electric fields now, just the transverse electric fields which constitute an electromagnetic wave. Here the field is pointing like this. Here the kink is in the upward direction once again. In fact, it's rather difficult to draw a 3D diagram. So let me draw a better 2D diagram. There's a transverse electric field. There's no electric field seen here. No transverse electric field seen here. See, there's no kink here, because you're in a plane that contains the acceleration vector. There is no kink here. There are slight kinks here. So this is the transverse electric field because of this accelerating charge. This charge is accelerating. There's a kink here, a large kink here, a small kink here. Let me draw these proper in magnitude. Let me reflect their magnitude here. The charge is accelerating downwards. I draw a circle here. I'm only drawing transverse electric fields. Here the field is large. The field is large here. Now this has nothing to do with the radially outward pointing field of an electric field. This is just a transverse electric field that is produced by the acceleration of this charge. Here there is no electric field. Here there is a kink. So there is a transverse electric field, but it's smaller in magnitude than the field here. Even smaller here. Even smaller here. Zero here. Here it's small. Smaller, smaller, zero. Small, smaller, even smaller. Small, smaller, smaller, even smaller. Now this electric field is transverse. If I have an observer here, that observer will see an upward or downward electric field. And this entire electric field is propagating outward with the speed of light, c. And associated with this electric field, there has to be a magnetic field. Now, since the propagation is in the outward direction, this magnetic field is pointing outwards here. Outwards, 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 outwards. What about the magnetic field here? The magnetic field has to point in the inward direction here. Because E is upward, B has to be in, so that the propagation is in this direction. Here the propagation is towards the left. This is the direction of propagation here. In this direction, this pulse is moving like this. But to the left of this charge, this pulse is propagating. So this, remember, this pulse is going radially outward like an explosion. It's an explosion. Radially outward explosion. So this energy is actually exploding in the outward direction. It's bursting out because of the accelerating charge. So this magnetic field on this side of this charge has to point in the downward direction. And there is no electric or magnetic field in a plane that contains the acceleration vector. So this entire diagram can be rotated in 3 dimensions. In all 3 dimensions, you will get a similar configuration of electric and magnetic fields. This is how an electromagnetic field is produced. And this electric field is a transverse field. It's called a radiation field. Remember, it has nothing to do with radially outward pointing fields of a static charge. Are these magnetic fields the same in magnitude? No. The magnetic field is determined by the electric field divided by C. This is something we learned from the previous class. E equals BC. This has to be true for Maxwell's equations to be satisfied. So, smaller E means smaller magnetic fields. Remember, in this particular case, since the charge is accelerating downwards, there is a velocity of charge that's pointing downwards. And whenever you have a moving charge, a magnetic field is produced due to a moving charge as well. And that magnetic field is given by the Biot-Savart law. So if you calculate the velocity of this, the velocity is pointing downwards, You calculate the magnetic field is pointing outwards here and inwards here because the velocity is downwards for the charge. So the charge has a velocity downwards, and if you use the Biot-Savart law, which is given by QV cross B, QV cross with B, QV cross with R, the direction of observation. Then this moving charge will produce a magnetic field that's outwards here and inwards here. So this Biot-Savart magnetic field happens to be in the same direction as the radiative magnetic field. But this is just because this charge is accelerating. This radiative magnetic field is different from the Biot-Savart field. Remember that. If I have a charge that is moving with a uniform velocity v in the downward direction, then it's going to produce a magnetic field. That magnetic field, as you all know, is going to be circular. It's going to point like out of the plane of the blackboard here and into the plane of the blackboard here. But this field is not the same as the field that I've drawn over here. This field falls off as 1 over r squared, because according to Biot-Savart law, this is QV cross r over r squared, mu naught over 4 pi, of course. So it depends upon 1 over r squared. This is a different field than the field that I've drawn in blue over here. They just happen to be in the same direction, because this charge is increasing its velocity. If this charge were decreasing its velocity, it was retarding, then this Biot-Savart field would have been in the opposite direction of the radiative field. Nevertheless, I have a radiative field, an outward surge of radiation of electric and magnetic fields that are mutually perpendicular to one another and which will cause the outward flow of energy. This is the electromagnetic wave. Questions? There was a question from the lady at the back. There is a here. I'm just assuming that the observer has a certain width. The smaller the width, the smaller will be this width. Okay? Yes. Yes. Saad has asked, in an electromagnetic wave that we generally deal with, we have fields that go positive and negative. Here the field is only going in the positive direction. So it's a pulse of energy with the field in the positive direction. So this qualifies as an electromagnetic wave. But it's not the harmonic wave that you are familiar with. So how do we produce waves of this kind? This means that we have to accelerate charges and then decelerate them and move them in the opposite direction. So let's see how we do that. Suppose I have a capacitor and I have an inductor. This is capacitance is C, this inductance is L. The charge on this capacitance is Q. Could be a function of time. Now if I write Kirchhoff's voltage law, which means that if I use Maxwell's equation, the Faradays law, E dot del across this path has to be 0, because it's a conservative electric field. Now this means that if I take the potential rise across this capacitor, which is simply given by Q over C, and there's an induced EMF here which is in this direction, because charge is flowing inwards. So an induced EMF will try to produce a magnetic field which resists the flow of charge, so it has to produce an EMF in the opposite direction. So this means that this induced EMF, I induced, is written as E induced, gives me 0. This is simply Faraday's law here, Faraday's equation here. So this makes me write qt over c minus, now this is L di by dt to this circuit. Now what is I? I is just the rate at which this capacitor is depleting its charge. It's losing its charge. That is constituting a current to this circuit. So that current is simply minus dq by dt. So if I insert this value of I in here, what I get is L d square q by dt square plus qt over c is 0. I just take this L here, I remove the L from here. This is a differential equation that I need to solve. This shows how charge is being depleted from this capacitor, how this charge is depositing on this capacitor. It shows the behavior of charge in this capacitor because the Q is the charge in the capacitor. So if I solve this equation, I can see what this behavior is. So this is a second order differential equation. You've already seen equations of this kind. If I solve this equation, I get charge on a capacitor is given by some A cosine of 1 over LC under root times time plus a constant B sine of 1 over LC under root T. So this is a second order differential equation. I solve this. This is what I get. Alright. Now if the charge on this capacitor was initially 0, then at time t equals 0, this thing goes away. This is 0, which means A is 0. So I can find out these constants from the initial conditions. I suppose that at time equals 0, charge is 0. This means that this A becomes 0, which means that my charge is given by some initial charge, some Q naught, some B, I call this B Q naught, some charge, sine of 1 over LC under root times time. This is the charge of the capacitor as a function of time. At time t equals 0, the charge is 0. At some other time, there is maximum charge. So if I were to make a plot of the charge on the capacitor, this charge is going to oscillate in time. And the frequency of this oscillation is going to be equal to this factor. This factor is, let's call it the frequency, omega or omega naught. This is given by 1 over LC under root. So this circuit has a natural frequency given by the product of the inductance and the capacitance under root inverse. Now the charge is building upon this capacitor. Here it's 0, it builds upon the capacitor, then it drops. Where does that charge go? That charge creates an EMF across the inductor. When this, okay, so this is the charge versus time. What about the current versus time? The current versus time is just going to be the derivative of this. That current is given by omega naught Q naught cosine omega naught t. So if this is a sine function, this is going to be a cosine function. This is the current as a function of time. To this circuit. Remember, at one point, when the charge on the capacitor is maximum, the energy on the capacitor is maximum, Q square over 2C. At that point, the current through the inductor is 0. The energy inside the inductor is half Li squared. So when this is maximum, the energy inside the inductor is minimum, 0. When Q is 0, the current is maximum, which means that all of the energy has now toggled onto the inductor. So there is a flip-flop of energy between the capacitor and the inductor. It's like a pendulum which is transferring its potential and kinetic energy amongst itself. So this is just like an oscillator. The energy is sometimes it's residing inside the capacitor and other times it's residing totally and wholly inside the inductor. And there's a constant toggle, flip-flop of energy between the inductor and the capacitor. Now if this is the current through this circuit, this is going to be proportional to the drift velocity of the electrons, right? Because I know that the current is simply given by the charge, number density, area of cross section of the wires into the drift velocity. So the drift velocity is oscillatory. If I were to plot the drift velocity, it's going to follow this yellow curve. This is the drift velocity of the electrons inside the circuit. Now if the drift velocity is oscillatory, it's going to have a cosine dependence. Now if I take the derivative of this drift velocity, what do I get? I get acceleration. The charges are actually accelerating inside this circuit. And if I were to plot the acceleration of these charges inside the circuit, now I'm plotting the acceleration. It's going to be an oscillatory function of time. Sometimes it's positive, sometimes it's negative. So acceleration is positive, negative, positive, negative. It's changing its direction, in other words. In such a case, kinks will be positive, negative, positive, negative. Move this charge in the opposite direction, you'll get kinks in the opposite direction. In fact, this radiative electric field is actually something you should be, I'll put up a derivation on the website. This radiative electric field is given by 1 over 4 pi epsilon naught minus q into A normal divided by C square R. I'm going to explain this in a minute. First of all, notice that the radiative electric field that's coming out from an accelerating charge has a 1 over r dependence. A static charge or a charge moving with a uniform velocity has a 1 over r square dependence. But this radiative field has a 1 over r dependence. So if I were to plot the dependence of the electric field due to a static charge, it will drop off like a parabola. But for a radiative field, the drop off will be less severe. It's going to fall off at 1 over r. That's why electromagnetic waves can propagate over longer distances, because the fall off is gradual. And it depends upon accelerations, one of acceleration's components. I'm going to explain this in a while. And it depends upon the speed of light as well. So this is the radiative field, the electric field. If I divide this by C, I get the radiative magnetic field. That will be 1 over C cubed, because B equals E over R, E over C. So this is how I accelerate charges inside a circuit. Those accelerating charges will produce a propagating electromagnetic wave. Saab, is that clear? But what I need to do here is, I know that this circuit has a resonant frequency. So what I would really like to do is that I have a capacitor and an inductor, and I have a frequency source, an AC source that is tuned at the right frequency, omega naught, that can drive a current through this circuit. It's just like a pendulum. I have a pendulum which has a natural length, L, and it has a natural frequency, omega. I know that T equals 2 pi L over G. This is the natural time period. The frequency is just going to be the inverse of this. So if I give it a kick at the resonant frequency, its amplitude is going to be large. However, if I kick it at some other frequency, it's just going to oscillate at a small random amplitude. So I can drive this circuit with a frequency frequency source omega naught that is tuned to the resonant frequency of the inductor and the capacitor. And what I have here is an antenna. So charges are accelerating inside this circuit, which means at some point in time this is a conductor, so all of this will get some positive charge, all of this will get a negative charge. But these charges are now accelerating, so the charge configuration is going to change with time. This is then getting negative charge, this is getting a positive charge. So charges are accelerating in this plane. This forms an accelerating charge which produces a radiative electric field as the one I've shown over there. This is how we produce electromagnetic waves. This is how we transmit waves. And actually this is how we receive waves. Now, two more points before we finish. I would like to explain what this E perpendicular really means. It's actually clear from this graph here, from this chart here. A perpendicular is the component of the acceleration in a plane that's normal to the line of sight. Here, I'm standing here. My line of sight is this. I draw a plane normal to the line of sight. So I'm standing here, I draw a plane normal to the line of sight. This acceleration is wholly and solely inside this plane. Let me redraw this figure on the other side of the blackboard. Let me redraw this in a more systematic way. I have an acceleration that's pointing downwards, A. Let me consider 2 points, a point here and a point here. And a point here. Here, this is the direction of propagation, C. Now this acceleration, if I draw this line here, this acceleration is normal to the direction of propagation. So the electric field here, the radiative electric field, is given by minus Q A perpendicular, which is all of this A, divided by C squared R. Of course, a 1 over 4 pi epsilon naught here as well. Now let's look at this point. This point, an observer is here. So the direction of propagation is this, C. Now what I would like to do, I would like to find out the component of this acceleration that lies in a plane normal to this line of sight. So what I do, I draw that plane. That plane is just this plane. This plane is normal to the line of sight. This angle is 90 degrees. So I find out the component of this acceleration that lies inside this plane. Alright? So if this angle is, say, theta, this angle is also going to be equal to theta. So this electric field here is going to be 1 over 4 pi epsilon naught minus Q into the component of A along this, which is A cosine theta. So this electric field is going to be smaller here because theta is larger than 0. At this point, this is the line of observation, C. There is no component of this acceleration in a plane that's normal to this line of sight. So the electric field here is going to be 0. So this, I've explained what the A perpendicular means. It's the component of the acceleration that is normal to the line of sight. The electric field is going to be largest here. The radiative field, largest here, intermediate here, 0 here, small here, slightly large here, and so on. So this is what the A perpendicular in that formula means. Now this electromagnetic wave carries energy with it. So I have an electromagnetic wave. Let's consider our slab again. The electric field is pointing in this direction. I have a spring and a charged particle plus Q attached to the spring. Suppose this length is D. Now what's going to happen? Of course this charge is at its rest position given by the spring constant. Now this body of this mass, this reservoir of energy comes in like an electromagnetic wave and it passes through this charge. Just skims through this charge, right? It just passes through. Now there's an electric field here. That electric field is going to impose a force on this charge. Electric field is pointing in the upward direction. So the force on this charge is simply going to be equal to QE. This is the radiative electric field. The field carries energy. This is the component of the electric field that's inside the electromagnetic wave. So this is the force that is acting on this charge. Now this reservoir of energy briskly moves forward because all of this is moving with the speed c. So the amount of time it interacts with this charge is just given by d over c. So this force acts for a certain time, d over c, and gives an impulse to this charge. So this is the change in momentum of this object, of this charged particle. The change in momentum, you all know, is given by force into the time. This is the impulse. The impulse causes a change in the momentum, which is given by this. Initially its momentum was 0. So the new momentum of this charged particle is simply given by delta P. The new momentum is QE d over c. So when this wave front or this reservoir of energy has moved forward, it gives a kick, an upward kick to this charge. This charge could be part of some matter. It's some matter in space. It's a charged particle in space. It gives an upward kick to this charge. And the new momentum that this particle acquires is given by P nu. So it gains energy. The energy it has gained, I don't want to call this E because this confuses with the electric field. I call it K. The new kinetic energy is gained, is given by P nu squared over 2m. That's just 1 over 2m into QE d over c squared. So this particle gains energy. That energy is proportional to the square of the electric field. So this reservoir of energy imparts energy to a charged particle. The energy that it imparts is proportional to the square of the electric field inside it. If this were a negatively charged particle, that particle will move downwards. Still it will gain this amount of energy because you have Q squared. If this is negative, it's the same amount of energy. So if it's a positive particle or a negative particle, it gains energy. So this wave carries energy with it. Remember, energy has to be conserved. So if it gives some of its energy to this particle, then the electric field that propagates out of this after this interaction has to have a smaller magnitude because the energy inside, harbored inside that reservoir has to go down. And it actually does happen. Remember another thing, this particle now gets a force in the upward direction. So it accelerates. So when it accelerates, it goes up, this is spring here, it comes down. So it becomes a harmonic oscillator, it starts oscillating on its own. Like a harmonic oscillator. When it accelerates, it radiates its own energy. Every accelerating charge radiates energy. Unless you're talking about atoms in which electrons are going around the nucleus, but they're not radiating energy because there's no lower energy level. That becomes from quantum mechanics. Anyway, this oscillating charge produces its own electric field. That is called re-radiation or scattering. That re-radiated field interferes with the original field to give you a smaller field. Now I have an opaque object. If I have an opaque object, I have light here, no light comes in here. But electric field can actually transmit to this object. The point is that this object is re-radiating energy, so which destructively interferes with the original electromagnetic wave to give me zero electric field here. This is what opacity means. The sky is blue because of re-radiated energy. Remember that this acceleration here, this is speed. Acceleration will be the derivative of this. You'll get an omega squared here. So higher frequencies will be re-radiated more. That's why the sky is blue. Because blue is at a higher frequency than the rest of the colors of light. Anyway, so energy is transferred. Is momentum transferred? Now if I have this charged particle that's moving upwards, so this is the speed of this particle. Because there's a force, there's a momentum, there's a speed that this particle picks up. Now is there a magnetic field here? Yes, of course there is a magnetic field that's pointing outwards. Now there's this particle that's going up and the magnetic field that's going down. So there has to be a magnetic force. That magnetic force is in this direction, Fn. QV cross B. If this were a negatively charged particle, negatively charged but velocity is downwards. Velocity is downward, field still pointing out. But it's a negatively charged particle, so even for a negatively charged particle, this magnetic force is still pointing in the right direction. So this object also gets a sideways kick, which means it's, now if you have an oscillatory wave, then the average momentum in the vertical direction transferred to this particle is zero, because this starts oscillating with a certain frequency. The average of a sine function is zero. But whether it's going up or it's going down, it's still getting a momentum in the right direction. So even though the average momentum in the vertical direction is zero, still this electromagnetic wave can bring in momentum and transfer some net momentum this particle to the right. To the right, yes. So electromagnetic waves carry energy and they carry momentum. This momentum is called radiation pressure. When electromagnetic waves come in, they give momentum to an object. That's why you have these solar panels on large telescopes that are space-borne. They can turn around because of the radiation pressure from the solar field. This is a minute effect, but it can be exploited. The last couple of minutes, I would just like to motivate you about the Pointing vector. Suppose I have a reservoir of energy, electric field E, magnetic field B pointing out. Now take a small volume in space, a hypothetical volume. This cross-sectional area is A. Alright. Now I know that inside a volume of space, there is an electric field density, electric energy density half epsilon naught E squared. And there is a magnetic field, half mu naught B squared. So the total energy inside space due to electric and magnetic fields is going to be given by 1 over 2 epsilon naught E squared plus 1 over 2 mu naught B squared. But B squared is simply E squared over C squared. But C squared is 1 over epsilon naught mu naught. So I get epsilon naught E squared. This is the energy per unit volume inside an electromagnetic wave. Now suppose energy comes in, a wave front comes in and goes through this volume. I would like to find out how much energy goes through this cross-sectional area per unit time. the amount of energy that goes through this cross-sectional area per unit time is given by the volume of this sphere if this length is given by c delta t. If I go in time delta t, a volume of space of volume A into c delta t will be filled. So what's going to happen is that the amount of energy S that goes through this cross-sectional area per unit time is given by this volume contained inside this volume of energy contained inside this reservoir, which is given by epsilon naught E squared into the volume of this object A C delta T. But you have to divide this per unit area. Since we're talking about powers, you have to divide this by delta T. So this is the amount of energy that pierces this surface of cross-sectional area A per unit area per unit time. And this is just the Poynting vector. So this A goes away, this delta T goes away, and I'm left with epsilon naught C E squared. But let me write this as epsilon naught C E into E. But E is simply CB. This means I have epsilon naught C squared EB. But what is C squared? Is 1 over epsilon naught mu naught. So this is 1 over mu naught EB. This is how we define the Poynting vector. Now this is a magnitude here. The direction of energy transfer is in the direction of the cross product of E and B. So if I put vector signs on both sides, I will have S equals 1 over mu naught E crossed with B. And this reinforces our definition of the Poynting vector that we used earlier. Alright, so this concludes our course. We're going to have the exam probably on the 23rd or the 22nd, I don't remember. Alright, so I wish you best of luck for the exam. It was nice having you in my class. I wish you best of luck for future physics courses. Have a great time at SSC. Thank you very much. Allah Hafiz.